Hi, my name is Sam Sandoval. I'm a faculty and an extension specialist at the University of California, Davis. So today I'm going to be talking about environmental flows. I'm going to be talking first defining environmental flows, then stream flows, then what are the relevant ecosystems that we're talking, some of the characteristics of in-stream flows. Then I'm going to be discussing or explaining the natural flow regime and some methods for determining in-stream flows. And I will provide some examples. So, what are environmental flows? So, when we are referring to environmental flows, it's a flow regime. I'm going to explain you what is a flow regime, but it's basically a flow throughout the year that sustains natural river functions while meeting human water demands. So, when we're talking about environmental flows, it's not only related with the environment or with ecosystems, but also trying to meet human water demands. And this was actually defined by Leroy Poff in 1997. So environmental flows in itself is this balancing or determine a flow regime, this kind of variation throughout the year that supports the environment the same as human objectives. So the flow regime, so the water quantity, quality, timing, it is a primary determinant of how a river functions and the functions that are beneficial for the ecosystems. We do know that there is a hydrologic alteration or that we have changed the flows due to human activities, and this has happened in every part of the world. So we will have consequences throughout the world. And similarly, that the natural flow regime. So we should be talking about a flow regime that sustains the environment, not minimum flows. This is not Mother Nature. The ecosystems evolve in these flows that change throughout time, throughout time within a year and among different years. So we should not be thinking about this flat line and what will be the minimum flow. It is basically a flow that has to change within the year and throughout the different years. And as we are talking about this, there is still, this is a very new discipline that is now evolving. So a lot of the people think about environmental flows that are beneficial for the environment, but they also include human objectives. Only considering flows for the environment, those are mostly referred as in-stream flows. So there is a lot of confusion between in-stream flows and environmental flows. It might be some technical terms, but the reality is that in-stream flows are those that are only focused on the ecosystems, what is living in the environment. So these are flow regimes, and this is basically what you're seeing on this graph. This will be these are flow regimes that are associated with water quantity, physical habitat, connectivity, water quality, and all of these flow regimes, this variation within a year and throughout different years, they will help to sustain, in some cases, to restore ecosystem functions that we want to protect for protecting, restoring freshwater and repairing ecosystems. So these flows will sustain ecosystem functions, will sustain activities that are beneficial for what is living in the rivers. A flow regime, and this part of flow regime, it refers to magnitude, timing, seasonality, and interannual variability. So that's basically what we're seeing here. So um, to be more specific, a lot of times we refer this to the environment. So we are trying to protect the environment. When we are referring to the environment, what specific um, what specific group of things are we referring? Those group of things are freshwater ecosystems. Similarly, a lot of people refer to these as riverine ecosystems, freshwater ecosystems. You're going to see a lot of those things in the jargon. And specifically, we're referring to some mammals, some beavers, some aquatic flora, some fish communities, some of the basic food chain, in this case, here's phytoplankton and zooplankton, and some invertebrates. Think that when we're referring to environmental flows or in-stream flows specifically in flows to sustain the environment, we are worried about what lives in the river and what lives along the river, along the riparian corridor. That is primarily when we're referring that to the environment that we want to protect. In the terms for the riparian ecosystems, what lives along the river, we're interested in plant communities, we're interested in invertebrates, reptiles, amphibians, snakes, birds that live throughout the riparian corridor. This is the primary objective of determining in-stream flows, sustaining what lives in the river and along the river. So in terms of terrestrial ecosystems, we are, yeah, those also benefit for having a healthy riparian corridor, having a healthy river. I agree, but those are not primarily studied when we're determining environmental flows. The ones that are primarily studied are these freshwater riverine ecosystems and then these riparian ecosystems. So again, talking about in-stream flows, so this is this part relevant to the environment. This will be the part relevant to flows. So when we're referring to flows, what type of flows are we referring to? The first thing is we're referring to quantity. And to be more specifically, we are referring to seasonal and interannual variability, how the flow change within a year, and how the river and how the flow change in that same river at that same location throughout different years, and how we're going to express those in terms of magnitude, timing, frequency, duration, and rate of change. So how much water is at a given time, at what time these specific flows happen, what is the frequency, does it happen different times through within a year, it happens only once a year, once every 10 years, how long does it last, is it base flows that last throughout the summer season, is it flows that are receding during the snowmelt season for a given number of days, is it just one individual flow, one individual storm that it just lasts 3 days, and the rate of change, it refers to how it it changes from one flow to the other. So in the typical one is the snowmelt recession. So when the peak of the snowmelt until the summer base flow, how how the river is changing from day to day until it reaches this base flow. That is the rate of change. So in terms of flow, we're referring to quantity while also referring to quality, and that should be adequate along the river corridor, not only one place or in the other. And we're talking here about temperature, pH, total suspended solids, dissolved oxygen, metal, salinity, and so on. Habitat. So when we're talking about habitat, um, for me the easiest thing is like think that you put some goggles on your eyes and then you stick your head into the river. How does the river look like underneath? What are the forms? What are the landforms that are in there? You have pools, you have riffles, you can see a river that is meandering. Does it look like a box? How does it look like? So those are the specific channel types, river types, and you have that, you have different types of geomorphology, how the river looks like as you are moving throughout the river network. Um, Rivers are not only rivers of water, they are rivers of sediment, they are rivers of water quality, they are rivers of things living. And in this case, in terms of sediment, you can see how water is also transporting this sediment and what is the variety of sediments that are in there. That is referred to sediment composition. And finally, some of the habitat is also created by trees, by trees that are falling into the river and that are creating these complex habitats. Um, Connectivity, and in terms of connectivity, I should mention that rivers, to have a healthy river, it has to be connected longitudinally from its headwaters all the way to the mouth. Um, that it has to be connected also transversally from riverbank to riverbank. Also, in this case, vertically from within the groundwater and surface water. So those are the three different components that the river has to be connected. A healthy river is connected. So when we're talking about flows, so the environment, it was this freshwater, riverine, riparian, and then not that much terrestrial, but it will get benefited. In terms of flow, we're thinking about quantity, quality, habitat, and connectivity. Those are the components of in-stream flows. So let me explain you about now. I'm going to switch gears. So those are kind of the ingredients, the main components. Think of this of who are you inviting to a party? It will be these freshwater and riparian ecosystems. And what will be the different things that you're providing as a menu? It has to be quantity, quality, habitat, connectivity, and so on. Now, let me explain you about the natural flow regime. And this is very important because a river is the primary, it is the primary variable that manage processes in rivers. Depending how much water is in there, it can transport sediment, it can deposit sediment, you can have good water quality, poor water quality, you can benefit certain species over others, and so on. The natural flow regime, so the flow regime that occur in rivers without any human alterations, it captures that seasonal and interannual flow variability. So it captures this variation within a year and throughout different years. And this natural flow benefits not only one species but the entire ecosystems. At this moment, I haven't mentioned some species in these specific examples, but the natural flow regime encompasses all of it because that's how these specific ecosystems evolve through time. So and the natural flow regime, not only it is in terms of quantity, but it also influences water quality, the food availability, and the interaction with other species. So some of the assumptions for the environmental flow, for the natural flow regime is that if you do not understand how can you benefit, support a given river, try to imagine what will be the natural flow regime in the absence of human, and that can provide you a very good understanding of what will be the requirements for that specific species. So that's one thing, and think that the native ecosystem there evolved through the natural flow regime for millennia. We have altered in the recent story, but yeah, the native flows that live, the native ecosystems that evolved there, they evolved through the natural flow regime. And similarly, the natural flow regime provides this a times test recipe to restore or to protect the environment that a given that a given river may be subject to. Something to mention is that this is the natural flow regime. These are 9 stream flow classes, natural stream flow classes that we have determined for the state. So we do know how the rivers naturally flow in California. That is extremely cool. So as I explained, some of the components of the natural flow regime might be low flows, might be these kind of peak flows. Here they are also called pulses, and these large flows. Sometimes they are called floods, sometimes are called peak flows. But this range and this variation throughout the season provided benefits for fish, for vegetation, for insects, for birds during the dry season, during these low flows, during summer, but also during the wet season, during winter, or during the rainy season, where it not only connected, in this case, provide adequate habitat for given species to benefit from the groundwater or that lives within the river, but also when you have these large floods, connected nutrients, bringing nutrients, expanded the channel, provided transported sediment. The river was always connected. Now, current alteration of of rivers have modified tremendously the timing and the magnitude of flows throughout the year. And, and basically that has produced some disconnections longitudinally, also sometimes vertically, definitely transversally on rivers. It provides very few habitat for sustaining during dry periods, but also do not provide enough large floods so you can keep vegetation on the sides. It has definitely altered, modified it has affected again these riparian and freshwater ecosystems. So when I was talking here about that it captures the seasonal and interannual variability, I was referring to this. So again, think that within a year you have low flows, summer, dry season base flows. You may have some pulses, first fall flush or the first rain of the rainy season. You have very large floods, and you have periods of transition from the wet season to the dry season. Typically, these are snow melt. This is within a year. Now notice that this changed within years. So you can see that this is a decade when we have 1 year, 2 years, 3 years, 4 years, 5 years, 10 years. And within these years, we have years that they were very wet. So for instance, these two, we have years that were not that wet, but they still have these very large floods that has this frequency every other year, 5 every 10 years as we're seeing it. But look, we also have drought years. And these drought years, they were also beneficial because during drought years, you naturally, the things that live in the river, so the freshwater ecosystems and the things that live around the river, along the river, the riparian ecosystems, they were stressed out, and only the native vegetation, only the native species were able to evolve and were able to live and pass these periods of stress. So not only wet years were beneficial, but also dry years, drought years. How cool is it? So so that's why understanding this natural flow regime can help get your head around how the ecosystems evolve, and this provide you a good opportunity, good um, understanding on how to restore or conserve the environment. So this is a very short story about in-stream flows, or flows that benefits the freshwater and riparian ecosystems, what lives in the river and along the river. Um, think of this natural flow regime, at least in the Americas, in the American continent, as pretty much before the European colonization. So before the European colonization was in the entire continent, we have pretty much rivers that were that have this natural flow regime. Yes, there is there are locations where it was verified that some of the tribes, the native tribes of the Americas, they build some infrastructure. Sometimes they actually build small reservoirs and divert water, but it wasn't the effect as significant as we are doing it since the European colonization, and to be more specific, since the 1920s, the change, it has a lot of change. So think that we're going back all the way to before the European colonization, and think that this is the flow that you're seeing as it is changing the months, and you're looking at a given river, and this is how the flow changes. Sometimes it increases, you have some storms, and the flow will increase and reduce. A large flood storm event that is bringing all this water, and then the transition from the wet season into the dry season. It was not until 1976 where we start kind of thinking about how to restore the environment, the ecosystem. The reality is that this environment, or environmental flows at the beginning, they were more focused on the water quality aspect. Um, Very recently, we are actually thinking about how to sustain the ecosystems, the things that live in rivers and along the rivers. The first idea was let's just put a minimum flow. And actually, Tenant, who wanted to help rivers, in one of his discussions, he mentions like, well, if we just leave 10% of the flow of the average flow of rivers of water in rivers, that will be very beneficial because we were depleting rivers at an enormous rate since the 1920s and even before. Um, that actually create this base flow flat throughout the years, throughout the year. And that really modified how the seasonal variability of this first storm that actually helped to provide a good water quality. These large storms that move sediment and bring also nutrients into the river so plants can grow, so you have food for fish. It also modified this snow melt recession that is a good cue for a fish to actually look for refuge and try to look for good places to survive the dry season. All what I told you, all those details were changed for a flat line that didn't provide the variability that it was needed for the native ecosystems. And later we thought about like, well, perhaps we can change this minimum flow into some seasonal varying minimum flows that also are not providing any of the functions that I mentioned to you. Then in the almost in 2000 in the 1997 says, well, actually how we can restore it is let's go all of us back to the natural flow. And again, here we are, humans or the society at large, we are here on the world, so it is impossible to ever all of us to set back and do not withdraw water from rivers. Another idea, and that is later in the 2010s, is by Brian Richter, the one that you actually read the book of Rivers for Life. And this is shaving the aqua, the flow. By shaving the flow is multiplying the natural flow regime by a given factor, let's say zero point 0.7 or zero point 0.8, and dwarf, so get a proportion of the natural flow. And that was to be more protective. Still, in some places, it might be very low compared to the natural flow regime. And then later in along those years, also in 2010, this concept of functional flows. So flows that can provide mimic certain aspects of the natural flow, but and try to address these functions, these specific functions for the river. This first fall flush or this first rainy store event to flush quality, some large floods to move sediment and to provide cues for migration, a good transition between the wet season and the dry season, all of this. But so for trying to provide to mimic these flows, but still leave some room for humans, for the society to extract water. So the difference between the black and the green hydrograph, that will be the water that can be used for humans. So as you can see, we have very recently 50 years of theory on this discipline. It is a very young discipline if you consider philosophy since the Greeks or I don't know, engineering since the Romans. This is the Romans. So this is a very novel discipline. So this is a very short history. Let me explain you some of the methods for determining these in-stream flows. So one are those that are called hydrology based and ecohydrology. And these are mostly statistical methods that try to determine through statistics some of the ecologically significant components, and components were those that I was mentioning here. I'm going to explain more of those in detail, and then mimic some of the desired functions, and in this case IHA, and that was some of the software that it was used before, very famous. Now we have eFlowstats, the functional flows calculator, functional flows that I'm going to be talking. Then we have hydraulic rating, and those are related with, so this is just relevant with flow. You're looking at a hydrograph and understanding what are the specific flows that will be beneficial for the environment. Those are the hydrology based. The hydraulic, they are looking at the arrangement of velocities and depths throughout the river corridor, and thinking that at a given height, you're going to have a range of velocities and depths that will be beneficial for the environment. This will be a basic concept that later evolved into this habitat simulation. And the habitat simulation, they link the spatial distribution of flow and velocities with preferential curves of given species. So to be more specific, there are species that like shallow waters, so not that much of a depth and not that much of a velocity. So what you're doing is going at a river, the river that you have in your mind to restore it, and then in that specific reach, in that specific portion of the river, measure what is um, the bathymetry, how the river, what is the topography under the water of the river, and then run some estimate what is the spatial distribution of velocities and depths at different flows. At a small flow, how much is inundated and what is the velocity of the region that is inundated. Similarly for larger floods and so on, and then relate those velocities to what will be the preference of a given, it can be a given fish, it can be a given amphibian, and so on. So that's how they relate those. And then finally the holistic, which are methods that rely on experts and experts with their knowledge, drawing from hydrology, these habitat responses or hydraulics, provide their assessment on how a river can be restored or conserved. So basically, these are the four main categories of in-stream flows. Now I'm going to be talking about these hydrology-based flows, and in this case, these are statistical methods, and you're going to use one on your assignment, where of all the with daily flow for different years, you start identify high flow pulses, low flows, large flows, and so on, and of these specific, now what we are calling flow components or specific flows that are distinctive in a hydrograph, start estimating what is the magnitude, when does it happen, how do they last, do they happen every year or every other year, what is the rate of change. Some of the advantages is that they are simple, they are very rapid to estimate, and rapid, you're going to see that is relative. It may take a year or so, but it's faster than the others. They are very visual as you're seeing here. Inexpensive compared to actually doing field work. Doing field work is it's actually quite expensive in terms of paying people, equipment, collecting data, and so on. They use most of the times available data, and they are focused on the whole ecosystem, not only one of a species. Some of the disadvantages that they are not that directly linked with the habitat of how the river look like. Again, if you stick your head into the river and see how the forms are, they are not explicitly related with how the river looks like under the water. It's just considering that the hydrology will bring all the benefits implicitly for the ecosystems. They are sometimes constrained by the sites in which you have stream flow data. So in this case, I'm just going to be presenting you one example that is functional flows. I've also worked with the natural flow regime and so on. And the idea for functional flows is the thing that you have these flows throughout the years. Now, think that in January 1st or in October 1st of all these years, you obtain the median value, the 50th percentile, the 25th percentile, the 75th, the 90th, the 20th. So you obtain of all the October 1st, what occur in the middle, what occur in the 10th position, in the 25th position, in the 75th, and so on. So if you do that not only for October 1st, but for every day throughout the year, you can get a picture like this. And this is the flow regime. It is think of it as the signature on how the river look throughout the different years. This variability in the horizontal in the y-axis is how it changed within years, and the variability in the horizontal axis in x is how the river flow, the discharge change within seasons, within a year. So of all of these things that you can now actually that you can focus in certain aspects of the regime that you know that they are beneficial for ecosystems. So what are the dry season low flows? What is the first fall pulse or the first rain event that you have? In this case, the dry season low flows can help you to sustain all the fishes, all the species that stay there and that went through this period of stress, that having not that much flow. This first fall pulse again is the broom. It will get rid of some of the water quality issues that are in the river, and it will start sending cues, start calling to the phone, sending a text message to uh, some of the fish that would like to migrate upstream. These large flows will provide is kind of the bulldozer. They will move sediment. They will rearrange the riparian corridor um, in the along the river. These wet season base flow, they provide this kind of high flows, so actually fish can migrate, all species can move. And then these spring recession flows, they will move from this wet season into the dry season in a way that is not so abrupt, not so fast, that they can actually, the riparian and freshwater ecosystems can move around. All what I told you, you can actually see that we have these biotic functions that are associated, or all these specific um, characteristics that I mentioned are beneficial for them. So you can actually overlay these functional flow components through all these different parts of the season that are important for frogs, for steelhead spawning. Something also that I want you to mention is that these can be associated to life stages. So we as a human being, we have different life stages. When we were newly born, when we were a toddler, when we were um, a, an infant, when we were a teenager, when we were an adult, and when we are an older adult, and so on. So this is the same, and we have different needs. It is the same here. These can be associated to specifically old adults that want to migrate. All of these, they will be enough habitat to support spawning. Some of these will be provide rearing, so adequate habitat for small fish to grow. This will be to move. So these can be associated to these life stages. They can also be associated to abiotic functions. And something that I was mentioning, to just wet the gravel bars all the well to do some bar scouring, so move for a large sediment, or to have floodplain succession, to actually inundate the floodplains and rearrange all the sediment throughout the rivers. So this, as you can see, functional flows can provide a lot of functions and bring back rivers to life. That's very cool, isn't it? So associated with that, you can draw these specific hydrographs that mimics these certain parts, these key functions, these components, and that will provide these functions that that are beneficial for biotic, for the things that are living within the river and along the river, and also to help to transform, to modify the physical habitat. And then associated with that, with all of this, you can estimate a specific metrics, specific quantities, and that is how you will ultimately characterize, provide a number to when this happened, when this end, what was the upper flow, the lower flow, and what was the peak of this flow, when did it start, how long does it last, where were happening these peak magnitudes, did it happen every year, did it happen every 5 years, every 10 years, how long did it last. So those are associated with this magnitude, time, and duration that are very important for the ecosystems. Okay, so now we're going to this second, that it will be the hydraulic rating, and then we're going to be talking about these other two. So specifically for the hydraulic rating, these are again based on hydraulics that can provide some that can create sufficient habitat conditions, and again it will be at a certain flow, the distribution of flow and depth. The disadvantage is that it's very simplistic. Sometimes inside a specific this can be related specifically to a restoration site where you want to know and you are modeling what are the arrangement of flows and velocities and how that can be beneficial for the environment. Think of it as when you're in your favorite spot. So this is underneath a dam. You can actually see the spill gates coming in, and that there might be the need to restore this area because it is mandated, because there is a part of the society or an NGO that wants to restore it. So what will be the arrangement of velocities and flows that can be beneficial for the environment? This will be one of it. If they are very localized. The next method or the next group of method is these habitat simulations. And again, let me just explain you that think that again you're seeing a river. You're actually seeing. Think of a river that you have in your mind, and that river. Think of how will how much of the river will be inundated at very low flows during summer, or after a rain, or when we have these atmospheric rivers and they are inundating even the floodplains, or when at the end of the snow season when we're seeing all the snow coming in. Not only think about the different levels of water, but how will be the distribution of velocities and depths given those different flows. So that will be this portion of here associated with that distribution. So if of the entire a channel that was inundated, how much of that portion was very low flows and very low depths, or large flows and large depths. Those can be associated with preferential curves. So curves that, and we have done studies where we are kind of identifying what type of velocity and depth some of the fish, like some of the amphibians, like what depth do we want to keep in the river, so we know that the roots on the trees that are along the riparian corridor can also tap into that water. So we have developed these curves that are associated with the velocity and depth of water, and that it can help us identify this at what given flow you may have good habitat, good conditions for adults or for juvenile fish. So they are related to hydrology and hydraulics, so the flow that is in there and the a range of depths and velocities. You also need to have a biological response, these habitat suitability curves, these preferential curves, and you can generate these different scenarios of flows and how they can benefit given species. These are called mechanistics. What that means is that you're thinking mechanically, you're using the mechanics of hydraulics, you're using Newton's second law and hydraulic principles, Manning's, to determine what is the range of velocities and depths, and then how fish are responding. These, unfortunately, these are because it's thing that we have monitored mostly endangered species, and these most of the times are focused on certain species, on certain target species. They are very resource intensive, and saying that is that you need to go and understand, have a 3D model of how does that reach, that channel look like, but think that you have to do that for the entire, for every reach of every part of the world. That's very intensive. This local scale now we have, I'm happy to report that we are now developing systems to actually make it regional. So let me explain you the flow form function. And that is related with how to relate flows to a specific channel types and geomorphology, that you can put certain preferential curves, certain functions, and estimate when can you generate improved habitat or when you're not gonna have that much habitat. So the red will be good habitat suitability and the blue one will be low habitat suitability. And this is what I was talking to you. So you have a range of velocities, and given the range of velocities throughout the riparian corridor and these preferential curves at a given flow, you can actually estimate where you're providing good habitat or not. Now, this, this specific method, the flow form function, not only relates this specific or does this relationship. The main difference is that this can be done regionally. This can be done actually spatially explicit. In order to do that, you not only need to know how much water is passing, and it can be through different flow regimes, but also what is the form of the channel. This response will depend on how the channel, the river channel look like. So we have generated ways, we have actually gone in through the field, did a lot of surveys and then generate classifications to estimate how river looks differently throughout the river network. From having rivers that are step pool cascades. So think of the form of the river as, again, putting your goggles, sticking your head into the river and see how the landscape, how the river look like underneath. Does it look like a meandering river? Does it look like these kind of very steep rivers that they kind of create these small cascades and jumps from one cascade to the other, generating these pools? Does it look like the quintessential these pools and riffles when the river kind of wides out and it gets deep, and then at certain points it start narrowing down and it gets at a faster velocity? So those are pool and riffles. Those we have gone into the and we have gone throughout California and generated different field sites, collected data at different field sites, and identified, classified those the field sites that we have, and then predicted throughout the river network how the channel would look like. Again, from these step pool cascades to these riffle pools that are widen and then shorten. Some of those can have gravel cobbles, so the different sediment size. Some of those have this kind of bed undulating, so the bottom of the river is undulating. Some of them can be boulder and bedrock, the bottom of the river. So we have identified how those are not only in this case throughout the Sacramento basin, but also throughout the state. So in every part that you're seeing here, we have actually estimated what are the different channel types that are every 200 meters throughout the state. This is such a cool, this is a very exciting moment for environmental flows. The last method is a method called holistic, and basically in this one what we're doing is what I mentioned. You provide this, bring the experts and then do some preparation before it, develop a workshop where you try to extract what will be some of these beneficial flows for the environment at given locations that you're interested, and then try to come up with a regime that will be beneficial for the environment. But this is mostly based on the expertise of people. They are focused for the whole ecosystem. Some of them can be explicitly flow physical, or some of them can be more hydraulics. And it depends on what is the data that you have available. Some of the disadvantages is that it relies on the expertise of the people there, on the judgment there. So that can be very risky, that you are based your opinion in the word of a person, the knowledge of a person, which in some cases can be perfectly fine, but in some others cannot. They are resource intensive and time intensive. You need to bring all these experts. They might be also expensive in that, and usually they are not spatially distributed. So think of it as like all the experts kind of working around trying to come up with these methods. In this case, some of the methods that I work is this building block method, where I've um, been seated with other experts, try to come up with these recommended flow regimes that based on the expertise that there is in the room, that you want to bring that expertise at a point where you can prescribe a flow regime. Um, they depend on the data. You need to have again some preparation of a workshop before you have this consultation. Then you get into the workshop and try to define these flow regimes. Um, and ultimately you want to generate these scenarios and hydrologic analysis to evaluate how these flows will actually can be implemented in reality. These are usually for restorations. And how they look, you go and a given person will mention that during February you may want to provide certain flows that will be from this flow that will have this depth and this average velocity that will be recommended for avoiding sediment deposition and so on. And then you can go not only that this was specifically for geomorphology, but you can think for invertebrates, vegetation, for fish. What are the specific drought and maintenance flows that you want to have for benefiting certain objectives of the Instream flow that you want to preserve. Again, we did something like this. In this case, it was in the Rio Grande, and we evaluated those at these different locations. These locations where you're seeing these points, there was determined this building block method and then run through a model to evaluate how much it improved the reliability of including environmental flows compared to the current way that things are operated. And the reality is that many times you're going to find out that is just about to redistribute the water that is available through time to also benefit the environment, which I think is good. We have a good opportunity to restore the environment. So finally, let's have this head-to-head comparison. So we talked about some of these hydrology bays, and some of them are more related or try to encompass the whole ecosystem. Some of them, they might be centered more in a given species. And some of them, as we mentioned, they might be more data intensive, and you will feel like this doing all the data analysis. Some of them might be very highly expensive. They might be more expensive than other ones. Um, some of them might be less reliant on the expert or more reliant on the experts. Some of them, they may have larger scale or smaller scale, physically based, and for certain, there are certain agencies or certain objectives that you want to make sure that what the flow that you're putting in the river will be beneficial for a given species. And in those, you need to be more physically based to know what are the physics of the system rather than just relying on that the flow will carry out for you. And some of them might be more spatially distributed. So with that, I would like to thank you for this lecture, and I hope you enjoy it.